Just let me a few minutes. Okay, so I think I am ready for everyone. So is everyone able to see the slide? Dr. Burgos, can you see my slide? Yes? Or is anyone listening to me? Or maybe I lost connection.
We see the slides.
Okay, thank you very much. Well, my presentation will be regarding biosolids, mineralization, and biofilter microbiota in a pilot scale system with rainbow trout, river prawn, and lettuce. This is an aquaponics pilot system that we have deployed in some high schools and also here in our university. This is a work that has been done by me, myself, of course, Elizabeth von Brand, Christopher Concha, Norma Perez, Camilo Merino, all of them from Universidad Católica del Norte, and Doctora Constanza Hanna, Dr. Carlos Cortés, and Engineer Alejandra Duran from INEA, both Chilean institutions. And all this research is belong also to our partnership with the University of Life Science from Norway and the Bursa Uludağ University as well from Turkey. Well, this is my agenda for today. I would like to introduce you about the problem and the explore solution that we have done. What is the aquaponic water quality that we have been reading? The experiences with the river stream and the lettuce, river stream that already Doctora Marina Cristina talked to you. Then we are going to talk about some mineralization approaches for the slush that the fish produce in the system. We're also doing some microbiome exploration to have an idea what kind of bacteria we have in our system. We are just starting to get that. And also would like to show you a little thing about the university and the high school that we are working with the aquaponic systems. So basically, the problem that we are facing here in the region where I live, Chile is a very long and thin country, as you may know. And we are in the north of Chile, about 500 kilometers north from the capital, Santiago. And as you are able maybe to see here, there is on the left and in the left corner, there is a map of the region where I am. The region is called Coquimbo. On, and at the very beginning of the year 2000, about half of the region was having or facing a scarcity of fresh water that is colored in red here. But 17 years later, pretty much the whole region is in red, meaning that there is scarcity of water. There have been some studies on the rivers that we have in the north of Chile, and I point out here the river that we have in our region. There are these three ones here. This is the Limari River, the Elqui River, and the Choapa River. And this graph is showing us what is the need for water to produce food or for use the water in other industrial processes. So what means in this case 43% means that we are requiring 43% more water than the river already had. And for the Limari River, we are asking for 80% more water than the river already had, meaning that our technologies that we're using maybe are not efficient in the use of the water, and we need to start looking for other kind of technologies to do an efficient use of this water resource. Because we were facing this scarce of water in the region, we developed some dams, so we were able to catch very fast the water that was melting from the ice in the mountains, and we keep it. So in this picture, you are seeing that this dam was pretty much full, and because it was too full, some of the water was spilled out from the dam. But at the next year or in a few years, the water was looking like this. So the we didn't have too much snow in the mountain, so the melting of that very small amount of snow was not enough to fill up the dam. So by year 2012, the dam was working at his 25% capacity. But the thing became even worse because by the next year, the dam was looking like this, pretty much pretty empty, a very small amount of fresh water available. Today we have a little bit more water, but still we're facing this situation with water scarcity in our region. In this graph, you are able to see about 100 years of recording regarding the annual precipitation in our region. So at the beginning of the 1900, we were having about 170 millimeters of precipitation. But as you see, along all the years, this line of the slope was negative, and we were even having even less precipitation, water from rain. And at the beginning of the year 2000, we were having about 80 millimeters of annual precipitation, and today we're around the 50, so even less than at the beginning. So every year we have even less water. And in the chart that I have here on the left and the right, actually, I want to show you how much water do you need when you want to produce 300 grams of fillet. Let's say you want some 300 grams of a hamburger that is delicious, maybe, but you want that, you might need about 4,500 uh, liters to produce 300 grams of fillet. But if you would like to have 300 grams of fillet from a pork, then you will need about 1,400 or so of water, liter of water. And and if you would like to have a chicken, 300 grams of a fillet of chicken, that will be roughly 11 and 7,000 of liters of water. So as you can see there, depending on what kind of protein you are producing, you might be requiring more water or less water. So, and here comes what we are working right now, because this region is also an agricultural region. The the agriculture engineers have been working, studying, and developing hydroponic systems. And I can show you the picture right here, basically with lettuce. And we, as a university, we have been working with something that we call it aquaponics. Maybe you are familiar with that. And the aquaponics, we actually are using the same water to grow lettuce and also to farm, in this case, rainbow trout. And of course, we are also including this little friend here. This is a river prawn that Doctora Maria Cristina Morales just spoke to us a few minutes ago. So to do that research in aquaponics, we set up different systems in different places. First of all, we started in our university. So we deploy 4 different aquaponic systems, actually three aquaponic systems, and the fourth was just a recirculation aquaculture system, just to compare how was performing the recirculation aquaculture system in comparison with an aquaponic systems. And in the INEA, that was the other research institution, we also deploy over there 2 aquaponic systems to do our research. We also deploy similar system in 5 high technical schools that I want to show you later in this presentation. So the idea that we have behind was to use a rainbow trout as our target fish. And that is very interesting because in this partnership that we have with Turkey and Norway, both countries, they also have rainbow trout, so we can share our knowledge with them without any problem. If we were using other fish, maybe it would be not that easy to share the knowledge. But basically, that we have here when we're doing aquaculture, the fish will excrete ammonia and also they will produce biosolids. So the ammonia in this system will go through the biofilter. These two towers here are working as a biofilter. One of them is working as a trickling biofilter, and the second one is working as a submerged biofilter. And the biosolids are captured in this settling device, and we keep the solids in this settling device for a few days. So to happen here a mineralization of the solid, and maybe with that mineralization, we are looking the productions of some nutrients and macronutrients that will be like this. So if we have these macronutrients, nitrogen, phosphorus, potassium, calcium, sulfide, and magnesium, those are very important for the veggies, in this case lettuces. And also we have micronutrients, iron, chlorine, manganese, boron, zinc, copper, and molybdenum. That will be very nice because those nutrients will be used for the veggies, and they will be taking out those nutrients and cleaning the water, and the water can be recycled back to the fish again. That is the model that we were looking for. And also we were exploring the river front to put those animals in this system, and we decided to put these river prawns with the lettuce in the same tanks. So we move forward on this idea, and with the other students that we have in our team that are more focused on instrumentation and control, they starting to build a system based on IoT. Sebastian Messina is already sitting and seeing the presentation. So you have any question at the very end, and he's still here. Maybe he can answer some of them. But Sebastian and Maximiliano, they were very interested in to design and build a system that can monitor some of the variables that we were looking could be interesting for the aquaponics. Some of those variables were atmospheric variables, and others were water quality variables. So in terms of the water quality variables, we were looking for the water temperature, for the water oxygen saturation, and also for the water pH. Of course, could be very nice also to have another sensor that would be able to record the conductivity, but we didn't have that in our system. And also we were recording for the atmospheric, the ambient temperature, the ambient humidity, and the light intensity that were measuring luxes. So basically, that was allowing to us to follow some of the variables on the system. Well, the first thing that we were doing here was trying to understand what happened with the water quality along the year. And here, this graph are showing several days for we're starting on October 2023 and finish the recording on March 2024. As you can see, the pH in these systems for the three aquaponics system and also for the recirculation water system, the pH was pretty stable around 8. The alkalinity was going up and down. That is very common in the recirculation system because the activity of the nitrification, meaning that we need to add some chemical to control the alkalinity. The temperature was pretty much stable. We would say in all these systems we have heat pumps, and we set up the heat pumps at the very beginning at 15 degrees Celsius, and then we increase it up to around 20 degrees Celsius. So you can see that those changes were following the temperature that we set up. Here we have a problem in one of our technical school that during the summertime, the water temperature, as you can see here, was close to 27 degrees Celsius. And when that happened, all the rainbow trout actually died. So temperature is a key factor when you're doing aquaponics or with rainbow trout. See, if temperature is too high, maybe you would like to change to other kind of species that are able for higher temperatures. But other water quality condition that we were following was the ammonia, and the ammonia was most of the time very low. We have some spike here for some reason, but mainly low because the biofilter were working nicely good. The nitrite was also low. Then we also have a little spike here for some reason. We were still wondering what happened. And the nitrate was, as we were expecting, was increasing along the time. That was pretty good because this will be the nutrients that the veggie will be using later. Also, we saw that the phosphate was also increasing in the water quality in the system. Sulfate is naturally present in our water, so it's nothing that the fish are really producing in there. Magnesium was also showing in some of the systems. So these are how they look like the letters production in one of the high schools, and these letters were coupled with the production of the rainbow trout. So you can see nutrients are in the water. We're also looking for calcium and potassium. Um, Basically, calcium was pretty much absent most of the time. The same thing for potassium most of the time. And this spike that we have here and the spike that we are also showing here is because we started to add calcium and add potassium when we were working with the alkalinity. So when we need to increase the alkalinity, we use calcium hydroxide or potassium hydroxide as a source for alkalinity, and also as a source to introduce the calcium and the potassium for the system. And here are the juveniles of the river stream that we were putting along with the veggies in our bed system. Here are the boxes and the bags with water and the shrimp that we were putting with the lettuce in there. Uh, how was performing our rainbow trout? This is our system that we were just putting together. Very old pictures right now. The fish that we buy from a nearby hatchery, those fish, the rainbow trout here are about 20 grams each one. Here we can see how was the growth rate, or during the time it took about 10 months for all the fish, actually between 8 months and 10 months for all the fish to reach 500 grams. That was our target weight. Um, Very nice and very interesting that the fish were growing and the plants were growing and the nutrients were present in the water. So these are pictures that we got from our system at the university. You see the lettuce over there, the little basil that we were working with. And here are the river stream that Dr. Maria Cristina was producing in her lab. Those are 3 months juveniles, and we put those juveniles in our aquaponics systems for them to reach a higher size. So they were 3 months. They were growing in our system for 5 months, and they got this size. We moved them into the veggies bed. So we're putting the stream over there, and on the top we put the veggies that you can see on the bottom over there. And later on, we were harvesting the shrimp that were growing with the veggies. So interesting scene over there. The question that we have on that time was how many shrimp can we put together with the systems where our lettuce? Because the shrimps are omnivorous, meaning that they can eat meat, but they also are able to eat veggies. So we did an experiment with different uh, stock densities. Some of the tank were having 10 shrimp per square meter, other 5 shrimp for a square meter, other 14 shrimp for a square meter, and some of them 17 shrimp for a square meter. And we were following during several days how was the length of the root of the lettuces that we have in the tanks to figure out how was the lettuce performing together with the shrimp, or excuse me, with the prawns. And we saw that at the smallest stocking density, the lettuces were growing much better than the higher stocking densities of prawns. So all these graphs showing that when we have between 5 to 7 prawns in the tanks, that was no problem for them to be growing in the same system where the lettuce were also growing. But if we have higher prawn densities, then the veggies will be pretty much without any roots. So here you can see some of the veggies that were losing pretty much all their roots, but over here you see more root developments in the other cases. So that was very interesting to start, and we are planning to continue with this research this year. And regarding the micronutrients, it was very difficult to find micronutrients that were in the system itself. So we were looking for zinc, molybdenum, copper in the recirculation system, and also we were looking for the same micronutrients in the three aquaponic system that we have deployed. And as you see here, the numbers or the concentration are very, very slow, excuse me, very, very low for each nutrient. A little bit of increment on zinc, but not much on molybdenum or copper. That is what we learned on what was going on in the water quality in our systems. In terms of nitrite, um, here says cycle 1, cycle 2, cycle 3, cycle 4. That means cycle of production of lettuce. Lettuce is take about 4 months, or excuse me, 4 weeks or 6 weeks to reach the commercial size. So these are 4 cycles of production. And as we move on, we see that basically in all the system, but in the system, in one of the aquaponics system, the nitrate was highly, but it's not a problematic for the fish of the stream to have 350 milligrams per liter, but basically was reaching about 100 milligrams per liter in all systems. That is very healthy for the lettuces. Calcium was also in a nice amount of quantity required for the veggies. So that is the interesting thing that you were able to see in the picture, that the veggies were growing very good. The only thing that it was is not too good is that in all our system we have a pH that it was pretty much close to 8, and veggies are very efficient into uptake nutrients when the water pH is between 5.5 and 6.5. But we were over 6.5. So maybe we should look for some way to reduce the pH in our system so the plant will be more efficient into uptake the nutrients, or maybe have an aquaponic system that people today call decouple, meaning that the aquaculture system is working isolated from the agriculture side, and the only connection will be for a few hours during the day when water with nutrient is moving from the aquaculture system to the hydroponic system. But in our case, at this time, we are working with a couple system, meaning that the water is moving from the fish to the plant, from the plant to the fish in an hour or so, several times a day. Well, this is the context. When we see an aquaponic system, we have basically our fish that we are growing. Those fish will produce some nutrients that are dissolved, and also they will produce some nutrients that are not dissolved. Those nutrients are within the solids that the fish produce. So what we have seen that other colleagues in other parts of the world, they are taking those solids and they work with the solids in a separate bioreactor. So in that bioreactor, they will produce the nutrients, and then those nutrients will be put back into the system. So the system will be then use those nutrients and also the ammonia that have been converted into nitrite in the nitrification system. And with all those nutrients, the veggies that are growing in the hydroponics system will be uptaking them. And of course, because they do that, the water will be in a good quality to go back to the fish. So basically, what we have done then is to take the solids and to figure out if we can do mineralization aside from the system. These pictures do not belong to us, but it's just to show you what basically you will do if you have the fish tanks. Then maybe you have some technology, let's say a drum filter that will remove the solids. The solid could be collected in a tank. Basically, if you want to remove some of the water, you can press those solids so that you can have some kind of sludge that is with less water. That is basically what the most companies will do here in Chile growing fish. In our case, we were doing from the collection tank, we would take some of the sludge and we were performing some studies to determine if what happened if we do the mineralization in an aerobic system or if we do it in an anaerobic system. This is a small video when we were just starting with the recirculation system. In this case, we didn't have any aquaponic, but we were having the two nitrification towers. And here is our radial settle. And all the solid that we capture, we move it into this bioreactor where we keep it for 24 hours with aeration. And after that, we stop the aeration so the whatever solid that we have in there settle down, and we just remove the water with the nutrient that we have in here. And then those nutrients, we put it into the aquaponics system. Basically, that was our first attempt for the bioreactors. But with that attempt, we started to do some research in a small vessels. Those vessels or the bottles that we have here, they were about 5 liters, excuse me. And we did an aerobic treatment and a facultative treatment, meaning that in this case, in the aerobic treatment, we put an airstone in each of the bottles, and we were looking at the nutrients on time. And in the facultative treatment, basically that we did is we removed the airstones, and we keep some device to keep the liquid that it was within the bottles in movement, but without any oxygen addition, to see what happens in those conditions with the nutrient production. So the question that we have at the beginning of this experiment was, is what will happen with aeration or without aeration? Which will be the best treatment to be able to remove the nutrients that are within the solids? The second question that we have is if we are able to do an incubation of this sludge in a sequential bioreactor that could be starting aerobic first and then anaerobic. Then we were looking if there was any effect on the mineralization process if we were having different sludge concentration. Let's say we started with a 20 milliliters of the sludge per liter, 30 milliliters of sludge per liter, 50, 16, and 80 milliliters of sludge per liter. We didn't did a higher concentration because back then we didn't have a strong blower to provide us enough aeration to keep the sludge moving in the water column. So we just finished up to the 80 milliliters of sludge per liter. And the last question is the one that it should be for. We were also wondering, as I said before, for lettuce or for the veggies, the best pH for them to be able to uptake nutrients between 5.5 and 6.5. So we were wondering if there was any effect and for the nutrient release from the sludge if we do the incubations of the sludge at pH near 6 or near 7. And we were measuring the ammonia, nitrite, and from the macro nutrient, we were looking at the nitrogen and phosphorus, sulfate, calcium, and magnesium. And from the micronutrients, we were following iron, copper, and zinc. And we were looking also at pH and ORP, the oxidation reduction potential of the water. So these are our first results. We were doing 3 replicates per incubations. These are bioreactors that are 2 liters. Um, in the left side, we have here the treatment that was aerobic, meaning with the air stones within them. And on the right, we see the anaerobic treatment without the aerations in the bottles. And basically, we see that iron and zinc, both of those nutrients, were not increasing in concentration, whether they were in aerobic or whether they were in anaerobic conditions. But in other cases, magnesium, it was disappearing if we have in aerobic, but was increasing when it was in an anaerobic condition. That's an interesting thing. Same thing for calcium. Calcium, even that the fish do not produce calcium, and the calcium was provided along with the alkalinity, we see that in aerobic condition, the calcium disappears, and in the anaerobic tend to appear a little bit. Phosphate, we see that it was more important, the presence of the phosphate when we were doing anaerobic in comparison with aerobic, just because uh, the the release of the phosphate requires two phases. First, it had to be into aerobic conditions, and then it had to be into anaerobic to be released into the water. So that was, we were wondering if we can have maybe two bioreactors and do the sequencing aerobic anaerobic treatment, because we knew that the release of phosphate will be after the process of an aerobic conditions. And about ammonia, well, the ammonia was increasing in aerobic conditions. And then we start looking what happened with the sludge if we were working at 20 milliliters of sludge per liter. And here, each of these graph will be having half of the graph will be doing an aerobic condition within the first 150 hours of incubation. And later or after those 150 hours, we continue the incubation of the sludge, but in an aerobic condition. Remember that the anaerobic for us was that we remove or take out the air stones. So any aeration, yeah, or oxygen that was in the system was depleting along with the mineralization process. But we can see here, when magnesium was increasing during the aerobic phase, but it started to decrease within the anaerobic with a little increase as well. Calcium was pretty much the same. Phosphate, as we were saying, was a production in anaerobic condition. Nitrate was in aerobic was disappearing, but during the aerobic anaerobic process was appearing, and probably because some denitrification that was growing over there. Potassium was more present during anaerobic. Ammonia was very low. pH was, as I said, it started with 7.5, then increased it to 8, but during the anaerobic process started to decrease a little bit. Our uh, RP was always over 0 when we were in an aerobic, but when we turned it into anaerobic, the RRP was reducing below minus 100 millivolts. This is important because in our natural water, we have sulfate. And the sulfate, when the RRP is below 150, about that much, the sulfate can be converted into hydrogen sulfide. And that hydrogen sulfide is very, very toxic for the fish. So if you do mineralization in an anaerobic condition, you need to look which are your RRP measurements so to avoid this sulfide to be converted into hydrogen sulfide. And this chart here, we have numbers that you can be following what happened, for instance, for any of the nutrients that we were looking at before we start the process and during the aerobic incubation, and also what happened during the anaerobic incubation. In some circumstances, you'll see that the nutrients increase or decrease, and others just maintain without any changes. But what we saw basically with the replicates, that was very difficult to have a very steady results. The replicates were very, we have a range that was a wide range of results, also meaning high deviation as well. So more research is needed to be sure what is going on in this situation. Well, if we increase now the sludge from 20 to 30 millimeters per liter, results are basically similar to what we saw, but of course we have more nutrients in comparison with what we're having with the 20 liters. So that is what basically that we were having here. Well, I'm going to speed up a little bit because we are reaching our time for our seminar today. And here we have an experiment where we were doing the sludge process with having a concentration between 60 and 80. So in this case, the 60 will be the green line here, and the 80 will be the blue lines. And if you follow all the graph, you will see that you will have more nutrients production in pretty much in all the experiment that we had when we were doing the 80 millimeters of sludge per liter. So that is interesting. But as I said, we didn't have a powerful blower to keep up all the sludge in the water column, so we couldn't uh, continue on expanding with higher stocking of the sludge. But the trend in here that we got is the more sludge you have, the more nutrients you are able to produce, and all the nutrients can be later moving into the aquaponics to provide the nutrient that the veggie will require. And in this time, we're also looking at the RRP, but as you see, the RRP never went below 0. So that was good because meaning that the sulfate became as a sulfate, didn't convert into hydrogen sulfide. We also did, as I said before, an experiment regarding the effect of pH in mineralization. We have a pH about 6 with the blue lines and about 7 with the red lines. Basically, for some nutrients, it was very nice when you were working in kind of in acidic environment. But for potassium, you can see here, oh, it was much better when you were close to a neutral pH. So what is showing this to us is that pH will be important when you do the mineralization. A sludge concentration and pH would be key factor when you are building or designing the bioreactor to do the mineralization of the sludge produced by the fish, and then you get nutrients that you can use in your hydroponic or your aquaponic system. So at the very end, now where we can see what happened with the aeration and no aeration system, well, we were able to see that the anaerobic was much better to produce nutrients, but because it was anaerobic, we were having small odors around, so something to take care of. It could be interesting to do a sequential bioreactor system, meaning aerobic and anaerobic later. Yes, we see that it's interesting to do so. And you have to have first the bacteria for those environments available so you can start very fast your bioreactors and the transformation of the nutrients. Do we see any effect of the large concentration on the nutrient production? Yes, we saw that. And also we saw that the pH have an effect. It will be better to do the bioreactor mineralization in an environment with more acidic conditions. Well, let's move on here to our technical school. We deploy, as I said before, the aquaponics systems, all of them the same technology. We deploy in 5 different high schools. The 2 research institutions were providing the trout or the river stream or prawn to any of these high schools, and also with the other institution, INEA, they were providing and advising about the hydroponic management. So this is basically the system. It has two tanks, the 1 cubic meter tank each one for the rainbow trout farming. It has 4 bed systems with the for the hydroponic productions. Here you see the picture as it look like. And this small unit here is basically having the 2 biofilters, the 2 towers. Here you can see them. The settling device to remove the solid that the fish produce. The sump where the water will be returning from the bed where the veggies are growing. And in this sump, we have a pump that take the water and move the water to the biofilters and from the biofilter back to the sump. And the other part of the water is going to the fish, from the fish to the settle, from the settle tank to the plant, and from the plant going back again to the sump. This unit you can put more fish tanks if you want. And also we created a handbook of these modules for the high school to read and to learn how to operate this system. This is our region. You see here where they were deployed along them. We were here, La Serena, Coquimbo. Some were in Ovalle, some of them in Punitaqui, and the southern one was located in Canela. In there, we were looking now how the lettuces were growing in those areas. We put about 30 lettuce per square meter, meaning that for each bed, we were able to put 90 veggies. Each bed had 1 meter width and 3 meters length, meaning that we have 3 square meters per bed. We were looking at the growth of the leaves and also the growth of the roots in those systems. And we were also measuring the foliar green cover. This means when we put the little plants, they look like this. But when the plants are growing, you see that they expand the leaf, and when they cover the whole bed, it will be the time to do the harvesting. The result that we had here were dependent on the location. This was January, February, excuse me, January 6, January 12, January 19, and January 23. 1 month of growing lettuce. Same date over here, 2 different places. Tongoy, that was in the middle zone of our region. Pan de Azúcar, also the middle zone of our region, but it's more inland, and Tongoy is close to the coast. And we see here that we got a better lettuce growth when we're in the system that was close to the coast, maybe because the temperature in the environment was colder in comparison when we move into inland, when the temperature is too high and maybe not good for the lettuces. Also, we were looking then how was the growing of the lettuces depending on which hole they were seed. This is we're looking here at the bed from the top. Here, these two here are 1 square meter, here the 2 square meter, and here the 3 square meters. So we put plants on each of these holes. We call it, this is column 1, columns 2, 3, 4, and 5. The water goes in right here and then flow all the way to the end, and the water goes out from this side. So we were looking then how the hydraulic of that bed system will be maybe affecting the growth of the lettuces. That means some kind of engineering. If you like engineering, you can also maybe start continuing doing this research. And we saw this when we were about on January 4, the plants were measuring about 45 millimeters of length, but some of the plants were larger, the ones that were in the column 5. For some reason here, all the plants that were here were the larger ones. The smallest ones were the ones that were in the column 3, means in the middle. That was happening. And a few weeks later, the trend was continuing the same. The larger was still the plant that were growing in the number 5, in that column, and the smaller one were in the middle, meaning that something was going on in the systems in terms of engineering or in terms of hydraulic. Similar thing. So we ran a research here to do a model, how was the water distribution. And in here you see that the entrance of water and the red colors and the yellow colors and green colors, meaning that we have an important water velocity here. But the light blue or the blue are meaning that the water, especially the blue, means that the water is moving very slow in there, and the light blue is meaning that the water is moving fast. So somehow we had different water velocities, and because that water velocities, we were having these different growths in the letters. Here you see the letters that were in the middle are growing slower than the letters that are growing in the lateral sides of the tank. So if you are interested in this, it will be nice if you can help us to improve the design and the hydraulic or the water movement in the bed where we are doing hydraulic, I mean, where we are farming the lettuces. In general, we have better performance in Punitaki, and that's the college, in comparison with the other places where we were doing the aquaponics system. That is, that it doesn't mean that the other places will be changing in anything to reach the performance that Punitaki has. It's just a geographical location. In other words, we shouldn't expect that the aquaponics will be performing exactly in the same way in different geographic places. So this study is showing us that geographic place or location will be also influencing the production of our aquaponics system. So this is our aquaponics and the hydroponic that we have in the institution that we call INEA. Just a general picture for you to see. I guess this will be our final reviewing here. We, in our university, we have 3 aquaponics systems, but in this experiment, we were following 2 of the aquaponics systems. And also we have a one recirculation system. So in our aquaponics system, we have these raceways with a division in the middle that allows the water circulation, kind of a circulation water. And in this tank, we have the rainbow trouts. Then we have the same training unit that I showed you before for the high technical school. We have a sump, a radio settle, and the biofilters. And we have 2 bed tables for the hydroponic growing of lettuce that are growing coupled with the fish tanks. For the recirculation system, the sizes are the same. The only difference with this aquaponics, and in this case, we don't have the bed system for growing hydroponic plants. So this research was done by Dr. Concha. I'm not expert in here, so I will try to do my best. But basically, we were using a machine that we call MineIon. And in that machine, we are able to run some experiment. And with the experiment, we were able to know the species that we have in our systems. And here's the methodology that Dr. Concha is following. He do the extraction from the DNA of the sample that he's taken with the microbes. Then they run that information in some genomics libraries. And with those genomic libraries, he can do the sequencing with the nanopore technology, with the MinION, as I said before. And with that, he's able to get the species that we have in our system. So he was looking what bacteria we have in our biofilter towers. As I said before, we have a biofilter that is working as a submerged biofilter, meaning that the media is always submerged in water. And then we have another biofilter that is connected in series that is working as a trickling biofilter, meaning that the media is not all the time submerged, basically is below a raining of water. And that is the trickling biofilter. So in here, A and B are the biofilter for the recirculation aquaculture system. C and D are the biofilter for one of the aquaponics system, and E and F are the biofilter for the second aquaponics system. And this big triangle here is telling us that basically there is very small variability of bacteria in terms right here is between 0 and 20. That's the variability of bacteria that we have in the two towers located with the aquaponic system. In the other system, the same thing, very small amount. And in the case of the recirculation aquaculture system, we see that there are more diversity of bacteria in the trickling in comparison with the one that is working as a submerged. That's a very basic information there. And if we move forward to see the variety of bacteria, so in this picture here trying to tell us that these two biofilters are located in one aquaponics, the other two one in the second aquaponics, and these two biofilters with the recirculation aquaculture system alone. And the same thing in basically what we found that in the submerged biofilters, I mean, these are the charts, the most dominant bacteria were those that belong to the class alpha proteobacteria. And the trickling biofilter, the dominant bacteria were those called gamma proteobacteria. And those groups, the alpha proteobacteria and the gamma proteobacteria, are related with the nitrogen cycle. So that's interesting because suppose those biofilters supposed to do the nitrification, and most of the bacteria that we found in there are bacteria related with that process. So basically, that is what we have for now, and we are continue doing that research to look at particularly what kind of bacteria are present and try to isolate those bacteria. So then we have strains of bacteria that are ready to be put in a starting new system whenever you need it. So those are the final results. The dominant bacteria that we have in the submerged biofilters for the recirculation aquatic system, you see a lot of bacteria in comparison for the submerged biofilter that was working the aquaponics. There was the most dominant bacteria were these four in the aquaponics submerged biofilter, but in the recirculation aquacultural system, there were more. Same thing if you look for the trickling or cascade type biofilter, there are more bacteria in comparison with the cascade or trickling biofilter working with the aquaponics. So those results, preliminary results that we have there, we don't have any answer why we have more bacteria in one system and less in other. Maybe the plants, the root of the plants are releasing some kind of antibiotic or are keeping some kind of strains of bacteria that we don't see in our recirculation aquaculture system because we don't have the plants in there. So I don't know, we are just hypothesizing some ideas, but we don't have any clear answer to that. We have now a project that we just started this year that we are focusing in to answer that kind of questions. And finally, just very quickly to close this speech, just to show you what we have doing with the high schools, where we are training the professors, we are also training the students, and we are releasing this technology that we have been studying in the university straight to the society. Here is Dr. Constanza Hanna from INEA, teaching the professor and student how to transplant the plants in the styrofoam bed before they move it into the hydroponic bed. With that, we expect that we are promoting social sustainability, teaching students and professors that are very connected to the society how to do aquaponics, and maybe they will be the entrepreneurs of this kind of technology pretty soon here in Chile. The system that we deploy in the schools are allowing the students to experience what they are doing, to share the result among the schools that are participating with us, and not just to share the result only with their classmates, but also to share their result among the other classmates in other schools. Also to understand the process that is going on in there, the process of growing the plants, the process of growing the fish, and also understanding the presence of the bacteria. They then generalize com- they can generalize just by comparison what they are having in comparison with the result from the other places or the other schools. And finally, they apply this several times a year because the lettuce uh, plant and harvest is growing on every month. So they are repeating and repeating several times and learning how to do that. So there are plenty of pictures and situations of us doing classes with the student, doing practices of, of moving fish, or in here where that we are seedling with bacteria the biofilter to start up a biofilter, or the student uploading or downloading the fish from the truck, or a professor here just preparing all this system to read the water quality of the system. All this information uh, you can be able to find out in our webpage from our project. And basically, this is all the colleagues that are working here in Chile. From the Universidad Católica del Norte, you already met Maria Cristina, who is doing some of this research. From India, Dr. Constanza Hanna, and also some foreign companies. Bofish is a aquaponic company from Mexico, and Entorno is another company from Colombia that are also helping us to improve what we're doing and to release the technology. We have a lot of projects in the past with different topics with several institutions, and also we have a network, what we call it Civiolat. And in that network, we have these two web pages that you can visit, and you can see a lot of information in there, including the seminar that we are having right now. And of course, we have this other international SDG network that is responsible of the seminar that we are having right now. And for that one, we have this other webpage. Please go to visit this one. In this case, this webpage will be is in English. The other webpage that I told you before is in Spanish. But please, both to visit the web pages and get whatever you can get in there. If you have questions, please do the question to us. We'll be very happy to answer. So that was all my speech for today. I'm ready to answer questions if you have any. Otherwise, I will say goodbye and have a nice day. All right, that will be all. As usual, I will say, Dr. Burgos, do you have any questions?
Yes, a lot of questions now. Yes, this is a good issue, and my congratulations for the presentation. It's very nice, very nice. You are an incredible professor. There is one of was your former student in this area. This is very excellent. It's very excellent conference. But now my question is about have you maybe some person, some researcher about your net have experience in tropical fishes?
Yes, and when mentioned that we were working with international companies, the last ones, Bowfish and the other company, oh, I forgot the name right now. What a shame that I forgot that. Yes, Entorno. They are working with tilapia barramundi as well. So
Yeah,
those would
yeah,
be, I
yeah,
would
yeah.
say, maybe more warmer fish. And also they have been, especially bowfish, they also were working, we were working with the river prawn, our river prawn that is from Chile and Ecuador and Chile and Peru only. But bowfish he was working with the microbiota Rosenberg. And in Brazil, they have been working with Lisa, there's a mullet. In
Yeah.
Brazil, they have been working with tambaqui.
Yeah.
Yeah, that
Now
would be
I
all
we
I would
we
say.
were working with tambaqui now. Now
Yeah.
we here in Ecuador with in my
Yeah,
university
in
here in
Brazil,
the
in
Amazon
Belo
region.
Horizonte, they have already 16 aquaponics system deployed for experimental trials, and the fish will be tambaqui.
Mm, because this is the second question. Is it possible to participate with this net with you, or maybe throw you
Oh, of course,
a
of course,
request of application?
everyone is invited to participate. You can. The only thing that you need to do is send us your request to be involved, and along with your request, a CV, your own CV. And
Yeah.
if you are a student, maybe also in your request, try to tell us, I would like to work, as you were saying right now, I would like to work with Tambaqui, who is working with Tambaqui. So I can tell you, oh, Dr. Ronald in, in La Universidad Federal de Minas Gerais, he's working with Tambaqui, and I can put you in touch, and then you can move over there.
Yeah, yeah, this
Or,
is very it's
or
very
if you
nice.
want to do, I don't know, let's say you want to do bioenergetics, bioenergy or something like that, I can put you in touch with Dr. Rodrigo Poblete here in Chile, or with Dr. Camille or Guray in Turkey. Or if you would like to do other things related from the agriculture to aquaculture, I can move you to Norway. So it depends. So what that is important when you write to us that you would like to be involved. Also, let us know beside your CV what area would you like to deep the knowledge so we can put you in touch with the right researchers.
Thank you a lot. And the other question is about your bacteria, because you to work now in microbiota and microbiome in different parts of the RAS system, yeah, RAS and aquaponic system, yeah. And you have any comparison with fish, with intestinal microbiome and different parts of the microbiome in the system? Because maybe
No,
there are a match for
yeah,
comparison. For example, I
no
don't
yet.
know.
No yet. In the slide that you're looking right now, here is Dr.
Uh-huh.
Christopher Concha. He's doing the microbiome studies right now. But also before, in our first seminar, I don't know if you were in the first seminar that was given by our partner from Norway, did you?
I didn't there.
Okay, well, anyway, you go to our webpage and look for the first seminar, you will see the seminar for the partner from Norway. And one of them was also doing microbiome. And I guess they are doing it longer than we have done it. So maybe he has looked at the intestinal, water, and other places in the system that can tell you what is going on. Is the same or is different? Also, Doctora Maria Cristina, um, I don't know how many years ago, with another researcher, they were also looking at the microbiome in the river prawn that she was working with.
Yeah, because my thesis degree now for doctorate that now I have I sent my borrador,
Mhm.
my preliminary
Grass.
thesis degree, my draft. Yeah, thank you so much. Because my director is Dr. Jaime Romero, maybe you know,
Mhm.
and we work with microbiota from Arapaima gigas.
Uh-huh.
But it's interesting to take the match. How about microbiome inside the aquaculture system, and what's happening inside with intestinal microbiome? There is so close in some cases or so different in other cases. And in this case, in particular case of aquaponics and RAS systems, we have different knowledge that we need to learn because we don't know anything about. And there is a good question for try to put it together. And in my case here in Ecuador and the Amazon region in Ecuador, because this is a so far region from big cities here, this is what happened with the other materials that you use in RAS system. For example, um, uh, low cost system for RAS. This is the other question, because the microbiome maybe in low cost material have problems with contamination. I don't know if it's possible, because
Yeah,
maybe the low costs are recycled. Like recycled have maybe PFAS. There are very contaminants for the environment and for the fish
yeah,
too.
maybe so. There are another group that is also doing this research, and that group belongs to the Aquaponic Association from the United States. So they are also doing the same studies in different aquaponics or commercial aquaponics that are spread all along the United States country. We are starting doing this because we found in our systems, basically in the aquaponic systems, that our fish never present any disease in comparisons with the recirculation system where we are able to see some diseases. So the people that work with plants in INEA, here in Chile, they told us that the veggies are able to produce antibiotic in their roots as a defense against the environment. So we are thinking that maybe in aquaponics, those veggies are producing some kind of antibiotics that maybe are moving around the whole system, and those are also maybe doing some kind of selection, what kind of bacteria could be and what kind of bacteria could not be. That's
And
another
maybe you
question.
have any identify what molecules, flavonoids or alkaloids or whatever molecules that are
Yeah.
there in these veggies?
No, we don't know yet. We are just, as I said, we are just starting this. And we just opened the door and we are just started looking at it. So it's if you are working on the area, I will tell you, okay, you have a site where there is no path, meaning that whatever you do will be the path for everyone to follow.
Yeah.
So it's a very,
Thank you
very
so
interesting.
much. This is
No
some
problem.
values information for me. Thank you so
Yeah,
much.
no problem at all. Anyone have any other question? Spanish or English will be fine. No problem with that. Well, if we have no more questions, I will let you go. It's right now in Chile, 11:30, about 11:30 a.m. It will be earlier in Ecuador, a 2 hour earlier, I guess, but it will be late in Turkey and Norway as well. So, well, I appreciate your time to be in this seminar. Thank you very much. And for the people that have been in the three seminars, if you would like to have some kind of certificate of your participation, please let me know and I can prepare that certificate for you so you have it for your CV. All right. So see you for our next seminar and enjoy your day.
Thank you. Thank you a lot.
Okay. Goodbye.
Goodbye.